Okay, welcome everyone. It's my pleasure to introduce Robert, who's going to be talking about non-rigid Kazhdan-Lusztig tensor categories for affine SL2 at admissible levels in quantum groups. Feel free to start when you're ready.
Okay, yeah. Thanks, Flora, for the introduction, for inviting me to give this talk. Yeah, I apologize if you already saw most of this talk at the Montreal conference, but maybe not everyone did, so we'll see. Or maybe I'll try to add a few new things that weren't in the Montreal talk. So let's see. Okay, so let me start with, so just to introduce some of the notation. So we're talking about affine Lie algebras. So we start with a finite dimensional simple Lie algebra. It's non-degenerate invariant bilinear form, which we scale appropriately. And then we have the affine Lie algebra, which has the these loop algebra bracket formulas and the central extension term. Triangular decomposition. So then, so we're interested in G hat modules at a fixed level. And the basic examples are the generalized Verma modules or Weil modules. So maybe I'll call them Weil modules in this talk since it's shorter to say and to write. So we're starting, they're induced from a G module, usually a finite dimensional G module, it doesn't have to be, but so we have the positive part of the affine Lie algebra act trivially, the central element act by the level K, and then there's the G action on M already, and then we induce to form a module for the full affine Lie algebra. And so mostly I think I'll mainly consider these Weil modules in the case that they're induced from a finite dimensional simple module, which is labeled by a dominant integral weight, highest weight lambda. When you induce from a simple G module, then you have a unique simple quotient in the Weil module, which I'll denote LK lambda. So with the definition of Weil modules, we can define the Kazhdan-Lusztig category the way that Kazhdan and Lusztig originally defined it in their first paper. Their first paper on affine Lie algebra tensor categories, I should say. So they defined this category to be all finite length G hat modules of level K and whose composition factors come from these LK lambdas. So that's the definition. Different people have different definitions of this category, but this is their definition. So I'm calling it the Kazhdan-Lusztig category. And then sometimes it's useful to have a shifted level kappa, which is the level plus the dual Coxeter number. And so then the famous theorem of Kazhdan-Lusztig is that if kappa is either irrational or a negative rational number, then this is a braided tensor category and is equivalent to the some category of modules for the quantum group at a corresponding value of Q. But then if we look at positive rational kappas, and it's pretty open as to whether you get a tensor category, but there are some results, but mainly is for this KL lower k category, which I'll use that notation to represent the subcategory of KL upper k, where the objects are modules for the simple affine vertex operator algebra of G at level K. KL upper k is going to be a category of modules for the universal affine VOA, which is not necessarily simple. So Arakawa proved that if K is an admissible level, then this KL lower k is finite and semi-simple. And then Kreutzig, Thomas, and Huang and Xinwei proved that it's also a braided tensor category. We also know that it's a rigid tensor category in many cases, although it's not always, well, we don't know that it's always rigid, but we expect it's always rigid. And sometimes it's a modular tensor category, but definitely not always modular. The conjecture would be that this KL lower k is also equivalent to some quantum group category, but it would be the semi-simplification of the category at this particular root of unity that comes from the level. And this conjecture is certainly proved in some cases. For example, when when the level is a positive integer level, for example. This is certainly known. So what I want to talk about today is some new results with Dinwei on the upper K category. But just for G equals SL2, K will be an admissible level. That means for SL2, that means the level is -2 plus P over K, where P is at least 2 and Q is positive, and you make sure they're relatively prime. So here I'm excluding the P equals 1 case. It's not because we can't do it, but because it's essentially already been done in Dinwei's earlier paper with Thomas. And in that case, what you get is a semi-simple tensor category. Okay, so the first result I want to talk about is that this KL is actually a braided tensor category using the vertex algebraic tensor structure of Huang-Lepowski-Zhang. Secondly, is that this category has enough projective objects. So that means for every simple object, you have a projective cover. So in case of SL2, the dominant integral weights look like n times alpha over 2 being the fundamental weight, n is an positive integer. So I will label the simple objects of KLK as LKN and use PKN for the projective cover. And I'll just mention for now, go into this a little bit more later, that this projective cover PKN is usually actually a logarithmic module, which means that L0 doesn't act semi-simply. Third result is that this category is not rigid. So not every object has a dual in this category, but instead but we do have some rigid objects. In fact, we can show that rigid objects are exactly the same as projective objects in this category. I should mention also that there's this other interesting recent observation by Allen, Lettner, Schweigert, Wood, that actually this category does have a weaker duality structure, which seems like recently people have been calling it Grothendieck-Verdier category structure. This weaker duality structure is what comes from contragradient modules, if you know what those are. But in this case, the unit object of the tensor category is not self-contragradient. So contragradient modules do not generally give you duals in this category. And I guess the fourth main result is that this subcategory of rigid and projective objects is tensor equivalent to the category of tilting modules for quantum SL2 at some root of unity. At the root of unity you expect, the one that's related to this level. So it's e to the pi I q over p. And so this last result, which is that tilting modules for quantum SL2 embed into this KLK as a subcategory of projective objects, actually gives us a universal property for this KLK category. So how that is supposed to work? Well, so the first observation is that when you do this embedding, there's a special simple tilting module, which is the two-dimensional one, which essentially generates the entire category of tilting modules for quantum SL2. So the functor sends that to the Weil module, which is induced from the two-dimensional SL2 module. So what that suggests is that this Weil module WK1 plays some special role in this KLK category. And so now this is basically the universal property. We suppose that we have some tensor category, C, which is an abelian category, doesn't have to be a rigid tensor category, but we assume that it has a rigid self-dual object X. So that means it has some evaluation map that sends X tensor X to the unit object, some co-evaluation that sends the unit object X tensor X. And because this is self-dual, you can compose these two maps and get an endomorphism of the identity object. And if that endomorphism is this particular scalar multiple of the identity object, it's like if you work it out, I think it's like -2 cosine q cosine pi q over p. This number here. So if you have this condition, then you get the universal property is that there's a unique right exact tensor functor from KLK to C. So basically, yeah, so I mentioned there's a universal property of the tilting module category up here. That universal property basically says that if you have such an object X in a category, then you get a functor from tilting modules to C, which is a tensor functor. And then because tilting modules embed in KLK as the subcategory of projective objects, you can use properties of projective objects to extend that functor F to this full KL upper K category. And this functor sends a special vinyl module WKN to the object X. So yeah, so that's the statement of the universal property of KL upper K. And so we can use this universal property to get a lot of interesting tensor functors, which come out of KLK, because there are a lot of categories that have objects like this X object. So for example, we can classify the KL upper K categories up to braided equivalents because, well, for example, if the two different levels, K and K prime, give you the same roots of unity, at least up to inversion, then they will have this scalar that you get when you compose EX and IX. These scalars will be the same. So you have a functor which sends WK1 to WK prime 1, and you also have another functor going the other way, so these categories are going to be equivalent. Although the braidings could be different, but we can calculate the braidings explicitly and determine, you know, whether this is an equivalence, whether it's a braided equivalence or a braid reversed equivalence or something different. So yeah, we also can get some sort of tensor categorical version of quantum Hamiltonian reduction because it turns out that there's a non-semi-simple tensor category modules for the Virasoro algebra at this central charge related to P and Q, which has objects that look like this object X with this kind of property. Probably the functor so there is an exact functor called quantum Hamiltonian reduction that takes you from affine SL2 modules to Virasoro modules. It looks like the tensor functor that we get from the universal property. It looks a lot like this quantum Hamiltonian reduction functor. So probably it's the same up to a natural isomorphism, but seems like we can't really prove that technically, but probably it's true. And then maybe the most interesting example is this, I guess what I call a non-semi-simple Kazhdan-Lusztig correspondence, which is an essentially surjective, but not fully faithful tensor functor from KLK to the quantum group category at this root of unity e to the pi I q over p. So in the case of Kazhdan-Lusztig's papers, they proved equivalences of categories along these lines. In this case, we definitely don't get an equivalence because KLK is not rigid, but the quantum group category is a rigid tensor category. So we can't possibly get an equivalence of categories, but we can get a functor, which is a tensor functor, which is essentially surjective. It's just not going to be fully faithful. But we can actually more or less characterize its failure to be fully faithful. Its kernel is basically coming from, the kernel of this functor is basically coming from this tensor ideal KL lower k, this category I was talking about before, this subcategory, this semi-simple subcategory. And then there's also, I also said this was an exact functor. The exactness is not immediate because the universal property says you get a right exact functor. But this extra duality, this Grothendieck-Verdier duality structure, this coming from contra-gradients can be used to prove exactness. Okay, so this is just a summary. So far, this is just a summary of the results on KLK. So now I'll discuss some of these results in a little more detail. So, so for now, just to discuss existence of tensor category structure on affine Lie algebra tensor categories, let's just allow G to be any simple Lie algebra, K any nice level. So this Weil module WK0 that is induced from the trivial one-dimensional G module is, so this has a structure of a vertex operator algebra, which we call VKG. It's the universal affine vertex operator algebra, not necessarily simple. So you can characterize this KLK category fairly nicely in terms of modules for this VKG considered as a vertex operator algebra. It's the category of finite length modules, which are grading restricted and generalized. Generalized here means that module is generalized if it decomposes into generalized eigenspaces for the Virasoro operator L0. And grading restricted means that these L0 eigenspaces or generalized eigenspaces are finite dimensional. And also there's some lower bound on the possible L0 eigenvalues. So these grading restricted properties are certainly satisfied by the simple modules LK lambda, which are the quotients of the Weil modules. Those are the composition factors of objects in KLK. So if you take a finite length module which contains those composition factors, then it is grading restricted and generalized, and conversely, grading restricted generalized module is in KLK if it has finite length. But the problem is that this finite length category is not, it's not clear that it has the right properties we need to get the vertex algebraic tensor category structure on this category. For that, it's more natural to consider C1 cofinite modules in general for a VOA, and I won't define what C1 cofinite means because it's well, I won't define what C1 cofinite means because for VKG in particular, it's quite natural. A module is C1 cofinite if and only if it's finitely generated as a grading restricted generalized module. So you can see the difference between C1 cofinite modules and KLK potentially is that you have finitely generated here, which is not necessarily the same as finite length. Possibly is a possibly weaker condition than finite length. So maybe before saying more about this, I will just recall exactly how we define tensor products of VKG modules, since they're not defined using the tensor product. They're not structures on the tensor product module because that doesn't preserve levels. Tensor product vector space, I should say. So we define the tensor products using intertwining operators, which are maps from a vector space tensor product of two modules into some space of series with coefficients in the third module. There's a commutator formula that tells you how the affine Lie algebra action interacts with the intertwining operator. And there's this important L1 derivative, L-1 derivative property that tells you how the derivative, the formal derivative of this series corresponds to the L-1 operator from the Virasoro algebra. And then we define the tensor product module W1 box times W2 in terms of this universal property for intertwining operators. This universal property where if you have an intertwining operator going into W3, then that uniquely corresponds to a G-hat module map from the tensor product module, the fusion tensor product module from W1 tensor W2 into W3. So 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 the definition is based on intertwining operators. So if you want to calculate what the tensor product modules are, you need to understand intertwining operators, and you need to understand intertwining operators to get maps coming out of the tensor product module. So I should say again that this is defined by a universal property, which means it's not an actual, this definition is not an actual construction of the module. We cannot be sure that a tensor product always exists. But fortunately, there's this nice general theorem of Miyamoto that says that for any VOA, the category of C1 cofinite modules is closed under tensor products. So tensor products do exist for C1 cofinite modules, and they are C1 cofinite. So again, for VKG, that means finitely generated modules. And then there's this nice result by Thomas and Zinwei, which basically says that all these tensor category constructions that were done by Huang, Lepowski, and Zhang, they do all work out if the category of C1 cofinite modules is the same thing as a category of finite length modules. So then you do get a tensor category structure where tensor products exist. There's a natural unit object, it's associative tensor product, and it's also commutative with some kind of braiding. So the corollary of these two results is that KL upper K is indeed a braided tensor category if every finitely generated module for VKG also has finite length, which is to say that it's an object of KLK. So to get the existence of a tensor category structure, we need to prove that every module is finite length. And actually, we don't need to consider general finitely generated modules, because if you have a finitely generated module, you can get this kind of filtration where the quotients in the filtration are Weyl modules. So it's actually enough to show that every Weyl module has finite length. So, the way you do this is that W1 in this filtration, you look at the lowest conformal weight space of W, it's a finite dimensional G module, so it contains a simple G submodule. And then W1 is generated by that simple G submodule, which is contained in the lowest weight space of W. That gives you a quotient of a Weyl module. And then you quotient out W1, and W2 mod W1 is constructed in the same way, and you keep going. And this filtration ends after finitely many steps because this module is finitely generated. So eventually you get all the generators. So it's enough to consider Weyl modules. So here's how we do this for Weyl modules. We need to show they have finite length. We do that by observing that the Weyl modules are quotients of Verma modules. So I use VKN. VKN is actually, so this is a Verma module for affine SL2. Actually, it's actually a Weyl module for affine SL2, but you get it by inducing a Verma SL2 module. So this is a Weyl module that's induced from an infinite dimensional Verma SL2 module that has highest weight n. So that gives you an infinite dimensional lowest conformal weight space in the Verma module. And to get the finite dimensional weight space, you have to quotient out an SL2 Verma module with weight -n-2. And the quotient of those two has the right lowest weight space, so it's going to be the Weyl module. So the Verma modules are definitely not finite length, but fortunately we don't care about them for this category. So the structure of the Verma modules we do know, which is, I think, in full generality, I believe this is due to Malakoff. You have these structures for the Verma modules. It's a little bit complicated. Generically, it's a little bit complicated with these kinds of diagrams. These diagrams show you which Verma modules embed into which other Verma modules. So if you start with some small value of m here, then this VKM contains all of these Verma submodules in this way. So if you want to look at WKM, you have to quotient out this VK minus M minus 2 submodule, and it contains almost all of these Verma submodules in it. The only one it doesn't contain is this 2p minus m minus 2. So that's why the Weyl module actually has length 2, where you have this simple quotient and this simple submodule coming from this. And if you want to look at the Weyl module for 2p minus m minus 2, you just get these two composition factors. For 2p plus m, you just get these two, and then for 4p minus m minus 2, you just get these two at the end. So in every case, you get a length 2 Weyl module like this. And then in the case that n plus 1, which is the dimension of the SL2 module, in the case that n plus 1 is a multiple of p, you have these simpler embedding chains. So in that case, the Weyl module is actually simple, because the Verma submodule you have to quotient out is actually the maximal submodule of the Verma module here. So you get a finite length property for all of these, and the conclusion is that we have a braided tensor category. So once we have a braided tensor
Robert, sorry, one question. Does everything you said up to that point generalize to any other Lie algebra, not just SL2?
Yeah, so okay, yeah, so I should say, let's see, at this point, this was all about, this was all general. Up to this point, this condition that you get a tensor category if every Weyl module has finite length. That is true for any Lie algebra, any level. But now we have to prove this for Weyl modules. So these diagrams here definitely only apply to SL2.
But maybe we don't have them, but they should also exist for other Lie algebras.
Yeah, they're certainly much more. They're certainly much more complicated, because the diagrams get as complicated as the Weyl group, affine Weyl group, which gets much more complicated beyond rank 2.
That makes sense. Thank you.
Yeah. So how to prove these? Okay, so now that we have a tensor category, we would like to compute some tensor products, maybe starting with Weyl modules. So there are a couple of key things key results that we have about about intertwining operators. And first of all, we have this kind of we have this property that intertwining operators induce SL2 module homomorphisms between lowest weight spaces of modules. So if you take an intertwining operator from 2 Weyl modules going into a third module, then you can restrict the intertwining operator to the lowest weight spaces of the Weyl modules, and then project the result to the lowest weight space of x0. So pi x0 here is projecting the intertwining operator to the lowest weight space of x. And I replace x in the intertwining operator with 1 just to get rid of the variable, the formal variable that's showing up in this series. And this is going to be an SL2 homomorphism. And moreover, we can show that if y is a surjective intertwining operator, which means that x is spanned by coefficients of intertwining operators, of coefficients of powers of x in y, then this pi of y is surjective SL2 homomorphism. So that means in particular that the tensor product module has a surjective intertwining operator coming into it. So its lowest weight space has to be a homomorphic image of M and 1, tensor M and 2, if these are the two lowest weight spaces of WN1, WN2. And then so this gives you some upper bound on how many intertwining operators that you can get. And we also get some lower bound, some actual construction of intertwining operators that Xinwei and I did a few years ago, and I generalized it a little more recently. And this is some kind of variant of some old results on intertwining operator constructions by Franco Zhu and Haisheng Li. So if X itself is a Weyl module, then under certain conditions, this map pi of y is actually a linear isomorphism. So any SL2 module homomorphism between lowest weight spaces can be lifted to an intertwining operator under some conditions. It doesn't always work, however. So for example, that means under some conditions, the fusion tensor product of Weyl modules is just the Weyl module that's induced from the tensor product G module. So under some conditions. So a special case of that is if we use a special Weyl module WK1, then we get a direct sum of two Weyl modules in most cases. And these conditions, in this case, these conditions turn into the condition that this is, again, this n plus 1 here is the dimension of the SL2 module. It should not be a multiple of P. If it is a multiple of P, that's the case where the Weyl module WKN is simple, and actually these conditions that we need here don't apply. So in that case, if WKN is a simple Weyl module, then the conditions do still imply that we get a surjective intertwining operator going to the I guess going to the plus case of this direct sum decomposition. We do get a module going, map going into WKLP. And the kernel is going to look something like WKN minus 1, but we don't know immediately that the kernel is necessarily equal to WKN minus 1. So to show that the kernel really is going to be WKN minus 1, we need to prove rigidity for this WK1 module. So now let me spend some time talking about rigidity for WK1. So that means we need an evaluation map, which takes us from a tensor product of WK1 with itself to WK0, which is the unit object of our tensor category. And we need a co-evaluation going the other way. And then we need this composition from W1 to itself, which involves the co-evaluation, the evaluation, and then some associativity in the middle. This composition needs to be non-zero, because then we can rescale either E or I as necessary to get the identity. And that's the rigidity condition. Maybe I should mention there's another composition that we also need to show is equal to the identity, but one can prove, well, anyway, it's not too difficult to prove that that will be the identity if this one is the identity. So we need a co-evaluation. First of all, the co-evaluation is kind of the easier one to construct because, well, we have this co-evaluation map at the level of SL2 modules. And then I said we had this pi of y map, which takes us from the tensor product, these two SL2 modules, to the lowest weight space of this tensor product module for SL2 hat. So that gives us a map from basically some vacuum SL2 module going into this tensor product module, and then the universal property of induced Weyl modules shows that this SL2 homomorphism lifts to an SL2 hat homomorphism from the Weyl module WK0 going into this tensor product module. So that's basically the easy part. Getting an evaluation is more difficult because we need to construct intertwining operators, and the intertwining operators are a little bit less obvious here. So if it's easier if P is bigger than 2, because in this case, I said there's some conditions for constructing intertwining operators between Weyl modules. In this case, the conditions are satisfied. So we get an intertwining operator going into WK0, which lifts the evaluation for the SL2 modules. And then the universal property of the tensor product module says that this intertwining operator script E corresponds to a homomorphism little e like this. But if P equals 2, this is more difficult because in that case, the conditions don't apply. We actually cannot lift the evaluation. We cannot lift the evaluation for the SL2 modules to an intertwining operator. So in that case, but we can get a map going into this other module, WK2. And when P equals 2, the irreducible quotient of LK2 is the same as the irreducible submodule of LK0. So we can still get an intertwining operator going to W2 first, then to L2, and then we include into W0. So this gives us a non-zero map, but it's not a surjective map because the image of this evaluation candidate E is going to be contained in the irreducible non-trivial submodule of WK0. So it's an interesting non-surjective evaluation map. So then we want to compute this rigidity composition. We want to show it's non-zero, so it's enough to show that some matrix coefficient of it is non-zero. So I wanted to show a few differential equations because this is something I didn't mention in the Montreal talk. So here is sort of the strategy for computing this matrix coefficient. You basically realize this matrix coefficient of the rigidity composition as the coefficient of a certain power of some variable in a certain series. And when you evaluate what that series should be, you end up with this kind of expression. It's a difference of two products of intertwining operators. One of them is this evaluation intertwining operator, and the other is this skew symmetrized version of the module vertex operator for WK1. And why are there two of them? One of them has an FV1 times V1. I should say F is the SL2F of the EHF triple. So here we have FV1 V1. Here we have V1 FV1. That's basically the co-evaluation for that's basically the co-evaluation for SL2 modules. That's what the co-evaluation looks like. So that's why we get these two different series. And they're two different series. They satisfy two different KZ equations using the L-1 derivative property for intertwining operators. We get two different KZ equations for these series. One of them, I mean, they both look similar. They're both second order differential equations with singular points of z equals 0, z equals 1. Both of them depend on this shifted level kappa in some way. But they're not the same, so we have to solve them separately, but fortunately they can be solved. We can actually solve explicitly in terms of hypergeometric functions. So these are the solutions. I wanted to write these explicit solutions down because I wanted to highlight this +1 here in the z, because that took Xinwei quite a bit of work to find that +1 and to actually get this solution. In retrospect, you can kind of see why there has to be a +1 here, because if you look at what that second series is, or is it the first series rather? It's the first series, and basically this evaluation intertwining operator cannot have any contribution in the lowest weight space of WK0 because the lowest weight space of WK0 is a trivial SL2 module, but if you look at SL2 weights of V1 and V1, then they add up to 2. So you can't have any contribution in the lowest weight space. So that's why there's a +1, because the first contribution comes from one weight space up. Anyway, I just thought I would point that out. It's not that important once you actually get the solutions. I should say this is the case for P greater than 2. The solutions look a little bit different when P equals 2. So anyway, these are the things we need to basically we need to take phi1 minus phi2 and then expand both of these hypergeometric functions as series in this different region as series in 1 minus z over z. And then we read off the appropriate coefficient and we get something non-zero, and that shows that this rigidity composition is non-zero. So anyway, that's basically the strategy here. And then let me just mention that when P equals 2, the solutions are a little bit different. Some of the solutions have logarithms in them, which implies in particular that this tensor product module is what we call a logarithmic module. These logarithms in the solutions of the differential equations are coming from the Virasoro L0 acting non-semi-simply. So this is what we do to prove rigidity for WK1. And now once we have rigidity for WK1, that gives us a lot of nice properties. So it gives us a lot of tools to work with when we want to compute fusion products. So we can return to computing this fusion product that I talked about before. We can show that there is actually an exact sequence where we have this irreducible, this file module as the quotient and this file module as the submodule. It's actually a non-split exact sequence. So this tensor product module is indecomposable. It's going to turn out to be projective. So let's call this module PKLP. And then because we have rigidity for WK1, tensoring with WK1 is exact, which means we can tensor this exact sequence with WK1 to get another exact sequence. We can compute both the submodule here and the quotient. They are both direct sums of a certain type. Both of these direct sums contain a WKLP minus 1 submodule, which implies that the fusion product module in the middle is going to contain 2 copies of this module, but then there are 2 more composition factors which combine into another direct summand, which we will call PKLP plus 1, and we get this kind of exact sequence for PKLP plus 1. Now we can do the same thing, tensor this exact sequence with WK1, and get another direct sum decomposition of the result, and we create another module which we call PKLP plus 2, and we can keep doing this repeatedly. And the end result is that we construct a bunch of indecomposable modules, PKLP plus 1m, which fit into this kind of non-split exact sequence. And if we want to describe the structure of this module in a little bit more detail in terms of its 4 composition factors, they look something like this. So these 2 composition factors, they are higher up because their conformal weights are higher up, and they correspond to this Weyl module quotient. These composition factors are lower down because their conformal weights are lower, and they correspond to this Weyl module submodule. And you can move between all of these different subquotients using the affine Lie algebra action, but you can also move horizontally between these 2 subquotients using the nilpotent part of the L0 operator. So I'm saying that these are logarithmic modules. There's a non-trivial nilpotent part of L0, which maps from this simple quotient to the simple submodule. Maybe I'll just say a few words about how we can prove that this is a logarithmic module, at least in the m equals 0 case. In the m equals 0 case, yes, that's sort of the easiest case, I should say. So showing that L0 is not semi-simple is equivalent to showing that the exponential of L0, which is this twist isomorphism, is not semi-simple. And there's this balancing equation that says a twist for PLP is this double braiding of these 2 Weyl modules composed with the twists of the 2 Weyl modules. So if we assume for the sake of contradiction that this theta is a scalar, and we know that these thetas are scalars, that would imply that this double braiding is a scalar. But then we can compute this double braiding here, and we would be able to, this double braiding would then basically be the square of these 2 double braidings. So this double braiding would also be a scalar. But in fact, this double braiding we can show is not going to be a scalar. It doesn't have the right, and it doesn't have the right eigenvalues to be consistent with this theta being semi-simple. So just a little bit about what goes into this. It's not, we don't really compute L0 explicitly using the affine Lie algebra operators. It's just some of these general tensor category properties that we can use to prove this non-semi-simplicity. Okay, so let me just quickly summarize. These are going to be the projective objects. First of all, the first p-1 non-simple Weyl modules turn out to be projective. Then all of the simple Weyl modules turn out to be projective, and then the remaining projective objects are these logarithmic modules that I was just talking about. So we have to prove that these actually are projective. The first step is to show that the unit object is itself projective. That's pretty easy. Second of all, we want to show that all these PKN modules are rigid, and that's now that we have rigidity for WK1, that is now easy because the PKNs are all direct summons of some repeated tensor product of WK1 with itself. So tensor products of rigid give you rigid, and direct summons of rigid also gives you rigid. Then there's this nice general lemma that says that in a tensor category with projective unit objects and a right exact tensor product, all rigid objects are projective. So that means all these PKNs are projective. And then all projective objects are going to be the direct sums of these PKM projective covers. So that means all projective objects are going to be rigid as well. So rigid and projective is the same thing in KLK. So that's briefly summarizing how we prove this nice property that rigid equals projective. Okay, so maybe last few minutes, I'll just say a little bit more again about this universal property of KLK. Now that we have some information about the structure of KLK, we can compare it to quantum group categories. So again, there's this root of unity, zeta, which is comes from the shift, basically exponentiating the shifted level. So then this rigid Weil module WK1 has intrinsic dimension minus zeta inverse. That means, again, if you do this composition of the evaluation and the co-evaluation, they have to be normalized to give you rigidity. If they're normalized correctly, then you can compose the two together to get this scalar. This scalar multiple of the identity. So that's called the intrinsic dimension, and it's the same, and this is the same as the intrinsic dimension of the two-dimensional simple tilting module for quantum SL2 at a root of unity. And as I mentioned before, this tilting module category has a universal property. Basically, if you have any tensor category with an object that has this intrinsic dimension, then you get unique tensor functor from the tilting module category into this category, which sends V to the object that has the right intrinsic dimension, which in our case is WK1. So we get this tensor functor sort of for free. Once we've proved rigidity, we get this tensor functor from tilting modules for quantum SL2. And we want to show that this is actually an embedding. And we can do that just by using the explicit structures of these two categories that we have already derived, especially this kind of, especially this kind of structure of the projective modules with this sort of length 4 diamond structure of the projective modules is something that you also see for tilting modules. So we can show that this is actually an embedding. In other words, it's fully faithful, and its image is indeed just a subcategory of rigid and projective objects in KLK. So now we have tilting modules embedded into KLK as a subcategory of projective objects. So that means if C is any tensor category with such a rigid self-dual X with the right intrinsic dimension, we get a functor from tilting modules to C. We think of tilting modules as being embedded into KLK as projective objects, and then we use properties of projective objects to extend this functor to the entire category KLK. So any W in KLK in particular is a co-kernel of some map between projective objects. So if you want to get a right exact tensor functor, you just have to send W to the co-kernel of f of f in the category C. And it's not trivial to show this really does give you a right exact tensor functor, but it does. So that extends f to KLK. So let me just summarize again the conclusion. What is this universal property? If we have any tensor category, I guess we should say that it has a right exact tensor functor, and it contains a rigid self-dual X with the right intrinsic dimension, then we get a unique right exact tensor functor f from KLK to C, which sends WK1 to X I guess maybe to guarantee uniqueness, we should also say it sends the evaluation of WK1 to the evaluation of X and the co-evaluation to the co-evaluation. So, and then let me just repeat again the examples that I mentioned before. So first of all, we can take C to be KLK prime for a different K prime, but if the root of unity for K prime is the same as the root of unity for K up to inversion, then they have the same intrinsic dimensions. The Weyl modules are the same intrinsic dimensions. So you get a tensor functor in this case, which will be an equivalence, at least at the level of tensor categories. Another example, again, as I mentioned before, we can take this category of modules for the universal of Virasoro. Maybe I should mention, yeah, so in this case, the X objects are these modules called, I think some of the mathematical physicists call them Katz modules. We actually have two of them because CPQ equals CQP. So that means we can get a functor from level -2 plus P over Q and also -2 plus Q over P going into the same Virasoro category. So this is like the Fagan-Frenkel duality for SL2 principal W algebras, I guess. Whatever. Anyway, we get these two functors and we can combine them into a single functor from the Deligne tensor product of these two categories if we want. And as I said before, probably these functors are the same as quantum Hamiltonian reduction, but not sure quite how to prove that necessarily, but it's almost surely true. And then again, there's this sort of weak Kazhdan-Lusztig correspondence where we get a functor from KLK to a quantum group category because KLK contains tilting modules. The quantum group category, of course, also contains tilting modules by definition, essentially. So we can extend that equivalence between tilting subcategories to a functor between the total categories, which is going to be exact and essentially surjective, but not fully faithful. So that's why I call it a weak Kazhdan-Lusztig correspondence. And maybe just let me mention this one more example, which I didn't know about until Azat mentioned it to me after I gave the Montreal conference talk a couple of weeks ago. He mentioned that he and Salur had constructed this braided tensor category as some kind of direct limit of temporally Lieb categories. And it looks like this category they constructed is actually equivalent to KLK SL2. But probably we can even show at the moment that they are equivalent as just simply as categories. Whether they have the same tensor structure, I guess, depends on whether the right objects in their category are rigid or not, which I'm not sure if they addressed. But this is one more example where probably we get some kind of tensor functor, and actually probably it's an equivalence. So probably this KLK has actually appeared before in a different guise, I guess. But so anyway, I think that's all I have, so I will stop.
Thank you so much. Thank you so much, Robert. Let me stop the recording so that we can ask questions.